Good afternoon. Hope everyone is doing great. And we are standing in between you and happy hour. We understand that, and we will try our best to have the session short. Right? And today we'll be discussing how OpenBMC can extend beyond compute. And I am Winston from AMI, and I'll be covering OpenBMC-based AI infrastructure management. It's happening today. The deployments are current. There are active deployments today in data center that's actively managing complex rack systems, right? And moving to midterm, Munir from Lattice Semiconductor will cover co-packaged optics management, followed by OBMF and OBMF ICP. And looking at longer term, Wim from NXP will cover hardware scalability and OpenBMC beyond data center. And here you can see a typical rack that are deployed in modern data centers. It has various devices like rack manager, PowerShell, and high-speed interconnect devices like UA-Link switches, co-packaged optics, general purpose AI and compute nodes, and CDU, right? And all of these devices definitely need out-of-band management today. And the Redfish, which has replaced legacy IPMA, right, has become a de facto standard for out-of-base management. And OpenBMC embraces Redfish, and it has support for various hardware interfaces, right? And it is highly modular and scalable. So these qualities make OpenBMC deployed in all of these devices for out-of-band manageability. And this and from a single code base of OpenBMC, right, we should be able to derive firmware images for rack manager, PowerShell, compute nodes, and CDU, right? And this unified approach tremendously reduces complexity, and it helps any team, right, to quickly come up with different flavors of OpenBMC for management. And let's see the evolution of the racks. And starting with legacy, you have top of rack switch and compute nodes. And currently it's evolved into disaggregated AI racks, where it has components like top of rack switch, PowerShell, compute nodes, scale-up switches, in-rack or side-rack CDU, right? And as the power consumption of the rack is projected to increase from 130 kilowatt to 230 kilowatt, the CDUs are evolving from in-rack and side-rack CDU to in-row CDU, and all the PowerShells are moved to a separate rack, and it's going to be called HDVC. And HDVC feeds a direct DC output to the all the devices in the rack, right? And in spite of all this evolution, the OpenBMC-based firmwares, right, will play a major role in out-of-band management for most of the devices in the modern racks. And let's start with Rack Manager. And Rack Manager provides a single northbound interface for all the devices it manages. And Rack Manager aggregates the Redfish API of all the devices, and it provides a single northbound interface for the any data center manager, right? And Rack Manager also, when it comes to security, it prevents exposure of less secure devices, right, to the larger management network, and it improves the overall security. And let's see, and Rack Manager can also be part of top of rack switch. It can coexist with top of rack switch, or it can also coexist with PowerShell, right? And let's see a few features of Rack Manager. When it comes to inventory management, again, it provides a single northbound API where it integrates the inventory APIs of all the devices and manages. So the user, when knows the inventory API, he'll be able to go navigate to the nodes depending upon his need. And when it comes to firmware management, the user can upload a full firmware block of all the devices that it manages. And once rack manager receives it, it can do a parallel firmware update of all the devices that it manages. And when it comes to telemetry, the user can upload the metric report definitions for all the devices that it manages, and rack manager can receives it and propagates all this configuration to all the devices it manages, right? And OpenRMC from the OCP working group is the one that defines the standard. And Brian from AMA is also one of the project lead for this working group. And we request everyone to contribute to this working group so that OpenRMC becomes an industry standard for rack management. So let's move on to PowerShelf. The PowerShelf converts the incoming AC power to the DC output. It streamlines power distribution, enhances efficiency, and it provides a stable output for the high density computing environments, right? And here the BMC, it's typically called as platform power management controller. And in typical design, power management controller talks to this power supplies via standard interfaces via Modbus and PM bus. There are certain design where the MCU or FPGA that sits between PMC and power supplies. And the communication between BMC and MCU and FPGA is MCTP or USB. And the MCU or FPGA in turn communicates to all the power supplies via PM bus, right? And there are two standard bodies that defines standards for out-of-band management. The first one is DMTF Redfish, and the second one is OCP Hardware Management Working Group. So these two bodies complement each other. Like Redfish defines the Redfish API specification, and OCP hardware profile, they define profiles, which defines subset of Redfish resource properties that needs to be implemented in various devices like PowerShelf, liquid cooling, and so on. And let's see an example how OpenBMC is evolved so that it is compatible with different devices. A few years back, there used to be a single monolithic URI for power, especially was defined for compute BMC, which had voltage, power consumption, inventory details, everything in a single monolithic URI. Then Redfish forum came up with the power subsystem, which decoupled resources into specialized sub-resources so that this power system can fit well into compute BMCs. The same power system works well with PowerShelf or any other devices in the feature, right? So based on how OpenBMC is evolved, now anyone should be able to have a firmware, right? Quickly can come up with firmware for PowerShelf. So let's move on to liquid cooling. Now, the CDU usually circulates coolant at controlled flow, pressure, and temperature so that it relieves the heat from the, it takes away the heat from the high density computer environments, right? And when it comes to manageability of CDU, the BMC resides in a separate DCSCM card, and that acts as a manageability plane, whereas MCU acts as a real-time control and safety plane, right? So here, BMC communicates to MCU via Modbus, and MCU monitors pressure sensors, temperature sensors, and also it even detects the leak. And the MCU also, or FPGA also helps in pump control as well as valve control, right? And the MCU has a closed loop flow control so that it maintains an optimal flow of coolant based on temperature and pressure sensor values, right? And the standard southbound interfaces typically used in any CDUs like Modbus with protocol RS-485, RS-232, or even with TCP. And I2C and I3C, and in few designs, we also see the CAN bus used to detect leaks, right? And when it comes to manageability, right, all the redfish resources are modeled under thermal equipment, and even there are support for Modbus today in OpenBMC, like password Modbus. So the basic frameworks are already available. Anybody should be able to use OpenBMC for CDU management. So next, let's move on to high-speed interconnect, especially the UA-Link switch. So the UA-Link switch is the upcoming standard which connects the AI accelerators, right? So that it provides high bandwidth and low latency memory sharing between the accelerators. And here, the pod is the centralized control, which does the orchestrations for all scale-up operations using a redfish and a GNMI protocol. Here, the down, you can see the nodes. These are all the nodes which has an accelerators, and that has also a BMC, and that's all connected via this UA-Link switch platform. And the UA-Link switch platform has a BMC along with UA-Link switch, right? And the pod communicates to the BMC, right? The node BMC via redfish. It can get inventory, or it can do out-of-band firmware update and normal out-of-band functionalities. And the UA-Link fabric interconnects all the accelerators. And let's take a scenario, right? For example, a user wants to do a DNA sequencing, right? And for that, let's say he instructs the pod, say that I need to allocate 10 accelerators to run my DNA sequencing job, and pod in turn communicates to the switch management service in the BMC, that it receives it, and it passes this information via UA-Link switch using UA-Link switch API, right? It's called Switch Abstraction Interface API. That's again defined by the UA-Link consortium, and UA-Link pulls the 10 accelerators together so that the user can run the AI workload, any job that the user wants to run, right? So this is the typical use case of UA-Link switch. And again, this GNMI protocol is, we are talking about so many standards from the morning, and this is another protocol that UA-Link consortium comes up with. And this protocol, we should be able to easily enable it in OpenBMC because the Octo already supports it. We should be able to enable it. And for the switch management agent service needed in the BMC, right? And so that's about UA-Link switch, and I will hand it over to Munir now.
Yeah, thanks, Winston. So next topic. So I think the way that we try to schedule this one is basically the near term is basically everything, all the protocols and implementation details is implemented already there. The midterm, which I'm going to talk about, is you don't have a lot of implementation details. There is some specs here and there, but there is no clear path about how this things is going to integrate with OpenBMC. And I think the long term that NXP is going to talk about is basically what we like to see. There is no existing framework or roadwork, right? So what I'm going to talk about today is one of the interesting points is the co-package optics and what we are seeing. So if you look at today, we're pretty much hitting the ceiling, right? Anything you talk about 200 gigabit per lane bandwidth, that copper is no longer is feasible there. So obviously we're hitting that line with the Blackwell CPU, Blackwell NVIDIAs and all those things, right? That's one of the big thing. So copper is pretty much out once you go that kind of transportation speed. obviously the power is pretty high at that speed. Power consumption is prohibitively high. Today, I think the copper is saying about 15 bit per picojoule of the data movement, which is co-packaged optics is moving to like 5 picojoule or even like 3 or 1. They have some roadmaps to that. So I think the BMC still is a problem, right? So we need to have the system management. So if you look at, there is two ways. Before, optics was a pluggable optics. So BMC it will get their information from a common management interface system and basically take it and do whatever it wants to do. What's happening when you do this package together in a single entity now, your optics and ASICs in a single one, then BMC is the only manager, right? You don't have that option that to go and outside of this one. So if you look at this 5 points here, if you look at the CPU compared to the CPU and GPU and how this co-packaged optics is evaluating, in a CPU and GPU, you already have a management engine that has been there for some time, right? It has been perfected, it has been going on. In a co-packaged optics, that luxury is not there anymore, right? So that means there's a lot more lift that we need to do. So there is no host side management bus. If you look at the CPU, you have management engine running there. Thermal loop right now is basically you need to manage both thermal side from ASIC side as well as your optics side. That's definitely life cycle is independent of the host. If you look at the network operating system, all those pivot inventory, telemetry through the network operating system, all those needs to be done right now for the BMC. Attestation has to anchor. This is one of the parts that BMC does today. And what we see is the redfish is the only fleet visible in surface. Basically, that's the only thing that we see that can make more sense. So if you go, the why CPU changed the management problem. So you have this, and if you have the pluggable optics that was before, there is a specification for that which is ELSFP, which is external light source from form factor pluggable. They have external for that. That is, if you have the single module owns ledger, that's a cell content module. It owns a ledger, it owns a modulator, it owns a driver, DSP management. It still has management data in out, MDII from host to module. It has some spec definition, but then when you go to disaggregate it across the substrate, co-packaged optics, and the optical engine sits next to the same substrate as the switch. Typically what we see is the ledger source is from external source and it's a multiple ledger source, right? Because each ledger is probably managing one lane. So if you're talking about 8 lanes or 16 lanes, you're multiple ledger source to DC. So multiple engines, multiple ledgers must be jointly orchestrated. And why, if you look at this today, this concept is pretty much new because we see the ledger coherency problem by the temperature. If there is temperature variation across the room, you may see this coherency issue with the ledger. You may see the wavelength changes slightly. It's not, when you talk about that kind of speed, that's a significant changes. There is a lot of error correction that we see today. Safety is another concern. So this is the CPU, changes the management problem. So in this case, this should be the model that we see. The BMC, the baseboard management controller, will sit between the external ledger sources. It's actually managing 3 things here, right? It's no longer just managing ASIC. It's managing the external light source that actually is providing this input, plus it also managing this optical engine that is sitting inside this co-packaged optics, right? So BMC has to do 3 things, plus I-safety, pairing this optical engine plus external light source together, and there's multiple of them. So this is the typically that we see on-host BMC board that needs to tackle. Now, if you look at, there is a 6th step that we typically people identified. Again, these is a hot swap pluggable, so they have to, anytime there is a hot insert or something happen, BMC need to detect. Controller need to read the CMI's identity. CMI's is common management interface specification for the CPU guys. They did capability pages, and they have to map this optical engine to what light source they're coming in. They have to map that. They also have to negotiate power, just to make sure that the line, the line quality, the link quality is up to the level what it needs to do. And BMC needs to make sure that the power is such a way that the link quality still stays what it's supposed to do, right? And they can go up and down. I-safety RAM, anytime you have a ledger. And then typically that we see monitor and telemetry. So this will monitor the DDM, VDM. This is the digital diagnostic monitoring. I think VDM is for something variable diagnostic monitoring per channel. It's going to read TX, RX bias. It also does another concept that introduces TEC, which is thermoelectric coupling. So basically, these things is cooled by the Peltier effect. As the Peltier effect that typically when you have two joined together, they can actually cool it down. So they use this TEC concept to cool it down. So that's something also they do it. And then temperature, error flux. And then anytime fault, hot swap or something, it's raise alert, allow, field, all those things that we see that BMC needs to do. Going back to the next slide. So if you look at here, this is what we see, that what is that extension? What is the BMC has today? What is to be extended? Again, this is the OpenBMC, not the BMC, OpenBMC. What is the extension that we see, right? So if you have to plug a CPO management into the OpenBMC, these are the things that we like to see. Definitely Redfish has to be implemented, more details, DBus interface, the phosphor D1 that can do the CPO manager. We still need PLDM, MCD support, extension of that. We need that CMIS spec abstraction on the OpenBMC that is defined by the spec committee. There is still I2C, I3C sideband interface, and then CPU hardware management of this external ledger and optical engines. And some of the key things that industry says today, there's some of the domains here, if you look at down below, like the domain signals and what is the cadence. Typically people do like 1 Hz, 1 Hz, 5 Hz, and all those things. Again, these are all industry standard today that we see that we need to add this in this OpenBMC domain. So this is just to show that OpenBMC is already there, but there is some more extra work that needs to be done to implement this Redfish, to implement this phosphor domain, to implement this PLDM, MCDB support they're looking for. And some of the things that what kind of interface that we're looking for, what kind of speed we're looking for. Nothing is impossible here. Everything is already there. I would say 60-70% is already there. So, but as I said, there's the CPO management still is a haphazard concept. There is some specs here and there, but the full implementation detail is not there yet. So this is our way of saying that OpenBMC could be a part of it, right? At the system integrated level. So my next topic is another one that we see a lot more discussion today called OBMF. So OBMF is basically is Open Boot Management Framework that defined, this is a transfer agnostic. But the big reason is that if you look at from the BMC development, we did run BMC, try to decouple the hardware software that never worked. We did the DCSCM, which is still didn't work because still you need to have this SCM and HBM pairing, right? So OBMF is actually trying to close this gap. So DCSCM moved your ROT secure boot logic into swappable module, but it's still pairing is needed, and OBMF basically is trying to close that gap. So it's trying to decouple the hardware and software. It tries to do basically independent of any kind of pairing, any kind of pin mapping, anything that you see today in the DCSCM is trying to basically take out all of this out, right? How is doing it? So there is an work stream. Again, I wrote down, there is, if you look at the GitHub, that's something that if anybody wants interested, they can look into there. They did a lot of work there. They had specification. They also have coding there that you can, basically run and open, OBMF code out of a RISC processor or something, and some kind of microcontroller there, and try to see what it is, right? So they have that. Although OBMF doesn't say what should be the exact protocol, but they are basically favoring USB and all those things, and I'll talk about that. But this is a work stream that delivered this OBMF ICP. ICP is the interface consolidation protocols. What that means, your BMC entity will sit, it will just talk one language, and then all those things that you want to have I2C, I3C, it will be all consolidated in an ICP spec. So that way you truly decouple now your BMC, because you don't care underlying hardware anymore, right? You don't care about physical layer, what you're talking about. We only talk one language, right? So it is right now is targeted at the DCSCM. So it's still DCSCM form factor. The only thing is that you have a BMC, and then you have something called that can translate your OBF ICP spec, right? That's what it is. And then it strives on DMTF trails. So it's still having all those MCTV, PLD, MSP, and plumbing. So it's basically saying that, hey, we don't need any kind of new network or transport. And it's a portable BMC firmware, right? As it is, it should be portable BMC. So these are the few things that I put together that specification-wise, again, it's nothing that is all available. There is, and I think, there is a CLA team that's much more advanced than what it is here. But I think this is what you have: OCP, ICP spec, 0.7. They are defining for USB device class. So they're basically saying from BMC to this ICP contributor, so there should be an USB link, and they're defining that USB link, right? They're also defining this MCTP spec of our OBMF. And then, as I said, like if you look at the GitHub, there's a lot of design docs, a lot of RDL files that somebody can go and implement it, right? So this is the one that I saw in Barcelona, that there is multiple implementation details that I saw the demo that is working on. There is some limitations on the demo. I can talk about that, but this is one of the things that NXP did. So if you look at here on the left side, on the left big board, I don't know if the cursor works or not, but yeah, that is an ASP2700 board on the DC SIM card. And then on the right side, you have an NXP processor. I think you have the name here, NXP MCX.N. So what this is doing is the ASP only talks by USB to the NXP. So it doesn't. So if you look at this OBF ICP, that's basically is an USB path. And then all the other downstream, like I2C, I3C is handled by this NXP1. So BMC is pretty much decoupled from everything that you see here, right? There are some other ones that they showcase in this OCP Barcelona. This is just one of the implementation details. I don't think this is still there yet. I think there is still a lot of concern here about, at least in the community, about the latency as well as how many controllers we need. I think this is still single controller. There is no USB 5 defined here. There's a lot of things still needs to work out on this one. But this is just one way that's showing industry that how this is moving. Again, I'm not sure whether OBMF is probably is going to go 100% or not. There's definitely some space here for this kind of application that when you want to plug and play compatibility, this is something to go. Will everybody in industry move to that way? I don't know that, right? But this is one way it's coming, right? And there's a lot of details, as I said, from the implementation side. There's a lot of details there. You have the codes and everything. I know one of my friends, he tried to implement these things, just run a RISC processor, get the design files from the GitHub and just ran it to see how feasible it is. It's a very simple exercise to try it out. And I think OBMF, their committee actually, basically encourages people to try it out. It's few hours of exercise just to see what it is. And they're open to have any kind of discussion if there's any issue that we see. I guess that's my last slide, Thank you all.
All right. Thank you very much for explaining our demo. Appreciate it. I want to go back a little bit to what Winston was saying, right? As you're scaling the use case of OpenBMC through, away from just the server into cooling and power and, all kinds of different widgets. I think as a silicon vendor, the challenge becomes different because now the hardware that does that management needs to be scalable as well. So I try to draw some random boxes there that, we can have a debate over that beer in a couple of minutes, whether there's more AI or more KVM or this or that needed in a cooling unit versus an AI server versus a traditional server, etc. But I think we all need to recognize that the one chip fits all OpenBMC use case model is probably going away. And that's a good thing because it shows that OpenBMC is going everywhere. It's exactly what you said earlier. So in our language, those chips translate into DMIPS requirements as a very ugly standard, but a standard in terms of compute. But we're seeing a range about 10x, 20x between the smallest and the biggest use case today. We see it in AI/ML acceleration. There was a question much earlier today on AI/ML making it into these BMC controller chips to either do predictive maintenance or eventually automated control, run an LLM, have an LLM manage the system locally rather than doing it remotely. So there's a different scale of AI/ML acceleration, as well as this different scale in I/O, right? Either by transitioning to USB, or what you observed earlier in the CDU, you may just have one Modbus link instead of 16 I2Cs to manage the motherboard. So there's all these different parameters that are driving us to different SoC implementation options. So that's one observation that we saw from our side. And then, one slide where, long-term vision, we're allowed to dream a little bit. And, where does this go next? Where does Redfish go next? Where does OpenBMC inherently go next? So my background over the last 3 decades, I'm old, is traditionally telecom. And I think to cut it short, right? If I look at what Redfish in the end is, it's a well-established management interface for hardware, right? That's what you boil it down to its essence. So anywhere where I have hardware, I need to manage it. So if our friendly friends from NVIDIA are working together with Nokia to build a 6G base station, I get a GPU at a radio unit at a cell edge. That GPU still needs to be managed. So what does that mean? Now, Redfish goes towards my cell tower. How do I do that? Well, now I think there will be a set of challenges, and it very much goes, to me, in my language, to in-band versus out-band management, or how do you carry management and payload on the same wire in different VLANs or otherwise. I think there's a lot of work to be done to noodle through that. I am not at all claiming that I know the answers, but we can see something like this coming in the next couple of years. I say by 2030, we'll be managing all kinds of edge compute, telecom, and similar boxes. So with that, I am very close to hitting schedule. I'll quickly repeat, what Winston, Munir, and myself are saying, call to actions. So I think, Winston, you're very much saying there's a lot of work ongoing that we all understand, in cooling units, power cells, etc. But even though there's pockets of standardization, it doesn't all work together. It's not all implemented. This year will be really busy getting going in that. Munir, you're saying correctly, the optical communication is probably one of the most critical portions of, let's say, an AI learning job. That monitoring thereof, therefore, becomes also important. Otherwise, your 3-month learning job fails all of a sudden. That means that OpenBMC needs to embrace optical. Can be done. It's not a huge deal, but still needs to be done. And your second point was OBMF, an OBMF ICP. Those standards are fresh. We see lots of activities of different people trying to implement them. I would like to see, a plug fest. Next time that we do this session, let's have everybody talk to everybody else on OBMF. That's extrapolating from what you said, Munir, but I hope you're okay with it. And then from my side, as I said, start looking at the edge, because there's a lot of work to be done there.